So before I start, I would like to mention that in the afternoon there's an XDS tutorial or presentation, and I got this tiny new USB stick for demo data. So the abstract says that I'll be willing to process with XDS some data from the audience. So let's say spontaneously, but so if there's anybody here who has data, please put them on this USB 3 stick and label them clearly with your name. Okay, so I put this here. So please come to the front, maybe after this talk, and then people can use this pick to put their data, and I'll try to look at those data sets over lunchtime and pick one of them that can be processed within the limited time of this tutorial thing. And I can also promise to look at the others with those people who supply these data sets. Okay, so this talk is about CC star. That's a quantity that provides a link between crystallographic model and data quality, and I'll broaden this topic a lot more, and I'll start with the basics because I am under the impression that crystallographic statistics, when it comes to data statistics, is extremely confusing. And it's confusing both to the novice users but also to rather experienced and old users like me, and it has taken me about 20 years to come up with a consistent understanding of what I'm talking about. So maybe I'm really barking up the wrong tree here, and you have to tell me about it, but I hope I will be able to simplify things to a point that everybody can make sense of those crystallographic statistical indicators that we are using and that we are talking about. So, okay. So the other day I went, so that's a month ago, I went to the PDE website, and it says it's almost giving us 100,000 structures. So if you go there today, that's more than 100,000. So that looks extremely nice, and the total number of X-ray structures is still rising. So as is the number in each year, it's growing linearly, I would say. And so I would say we are doing so well, but the question is, are we really doing as well as we could? And what I'm trying to say is we are very confused. We could do much better by really understanding what the indicators that we're using. And so to just start with the worst of these is our merge. And I've just gone through the literature and collected some of them and put them into some, they have no real relation here to each other in this slide. But I mean, to make sense of all of these and all the others that are not mentioned here is a difficult task. And as I said, 17 years ago, I published something about something very close to our PIN, and our means is actually defined by Eddie Carpus and me. And CC1.5 is the latest edition. So it's not about finding more indicators and publishing something about this, but rather what conclusions can we draw from these indicators? What is their relationship? And this took me another 17 years to really understand. So this is why I'm here today. So the topics today is signal versus noise, very simple. Random versus systematic error, accuracy versus precision. I can almost skip over this because Jim has already prepared this very nicely. Unmerged versus merged data. This is probably my main point. So these are two different concepts, or this is a concept that you really need to understand to make sense of the indicators. And finally, R values versus correlation coefficients, yes. And then, I'll specialize a little bit in the last part of my talk on the choice of high resolution cutoff, just some discussion in this area. Okay, so start with signal to noise, signal versus noise. So we all like to have a strong signal on a small background of noise, but as we all know, to high resolution, the ratio becomes much less favorable, and at some point we reach the resolution or the data quality where it becomes impossible to extract the signal from the noise. This is just taken from James Holden, and because it's just so easy to understand. So actually, when we talk about noise, what do we mean with the word noise? Yeah, we should realize that noise is a different word for error, and there are essentially only two kinds of errors that are of interest to us. And this is random error and systematic error. Those two sources of error exist, and we'll have to deal with them. Now, the main point to know about random error, and I'll give some examples for this, is that random error is always associated with quantum mechanics. Oh, that sounds very complicated, but we'll see the examples in a minute, and we'll see that they are not so complicated after all. Whereas systematic error is always associated with some technological aspects of our experiment, for example, the shutter, the crystal, or macroscopic features of our experiment, like the crystal. Yeah? And examples for random error is the photon emission from the crystal. So suppose the beam hits the crystal, photons can come out of this, but nobody can tell us when a given photon will be emitted from a crystal, because ultimately quantum mechanics, quantum electrodynamics will be able to tell this to us, and it will give us a probability distribution, a certain probability that in a given point or a period of time the photon will emit it. And this is where Poisson statistics comes into play. Same happens in the detector, where the photon gets absorbed or is not absorbed in the detector. You cannot predict this for a given photon. You can only tell the probability. This is another source of a quantum mechanical random error. And finally, all semiconductors, it's the electrons that do the job, and these also obey quantum mechanics. Now, more interesting for us are the systematic errors, and I tried to divide them up into different sources. So the blue lines here refer to the beam line setup, the experimental setup. So that's mainly the beam instability in its flux. It may become weaker and stronger as a function of time. It's ultimately, if you could monitor this very accurately, we could use this knowledge in data processing, but nobody does this. So it's not just a systematic error that we'll have to cope with in one way or another. It also changes its direction. Then there's the shutter jitter, so the shutter just doesn't open at the right time, it doesn't close at the right time, these things. Finally, and we already almost discussed this, the vibration due to the cryostream. We shouldn't neglect this. This is really one of the biggest, or in many cases, this is a big source of systematic error, really decreasing the quality of our data. Then comes the crystal split reflections. We've all seen those ugly reflection profiles, secondary lattices and so on. Absorption plays a role, radiation damage, which is probably the worst of all of these. And finally, then comes the detector with all kinds of sources of error, the dead time, shadows on the detector that are not masked, and so on. Dead pixels, hot pixels. And finally, the software, data processing software, whether it's called MOSFilm or HKL 2000 or XDS, the software makes some assumptions about your experiment. It tries to model the experiment, and the model is always ideal, whereas the real experiment is real. So there is always some discrepancy, and there is no way that the software can know everything about the experiment. So this will result inevitably in systematic errors. And probably the list could be continued. Okay, so now we have seen all these different kinds of noises, and we have to add them up. So how do we add up errors? If we have two errors, the same amplitude, we add them up and get a total error that is 41% higher. Well, this doesn't look right mathematically, so the real equation is down here. So this is adding adding up the squares of the errors gives us the square of the total error. So to correct our equation here, we have to insert those squares here. This is also something that Jim has been talking about already, so you should know this. I don't need to ask you about it. Now, if we have two sources of error that are not the same in amplitude, one is 3 times bigger than the other, then the stronger one takes over, and this is more visible if we say, okay, one of them is 10-fold higher than the other, then you don't see the smaller source of error in the end result. Almost you don't see it. You can take account of it, but it's not so big, it's not so visible anymore. So this law of squaring errors and adding them up is only valid if the errors are really independent from each other. This is the whole concept here. It's very easy as long as the errors are independent. If they are not, it becomes very complicated, because then you need to know their covariance and stuff like this. Okay, so how do random systematic error depend on the signal? What you need to know is that random error always obeys Poisson statistics. So that means the error is actually the square root of the signal. It's related to this, and you have to take the right square root, so to say, square root of the variance of those terms that go into the signal. In that case, mostly the peak and the background, also explained by Jim. But we'll just note this square root law here. Whereas systematic error is always proportional or close to proportional to the signal itself. So the error can be approximated by some constant x, which is in some range. It's a few percent of the signal. So yeah, a few percent of the signal is always the error. And this applies to all those sources of systematic error that I had in the other slide, that had these colorful lines in it, right? So all of these give you a certain fraction of the signal as an additional source of error. None of these give you a square root type of error. This is very important. So we need to add those types of errors. All those error sources have to be added up. Hopefully they are independent, so we can just add up the squares. And we'll find that at high resolution, the random error almost always dominates. This is because the fractional error, the systematic error, that's only a tiny fraction of the signal, which is already weak at high resolution, but the contribution of the systematic error at high resolution is even weaker. Whereas at high resolution, the square root may be sizable compared to the signal itself. So at high resolution, we are mostly dealing with random error. At low resolution, conversely, it's the systematic error that dominates. It's not the random error. And there is one exception to this very simple rule: radiation damage, the worst of all kinds of errors. This does influence the high resolution, as we all know, but it does also influence the low resolution. So it's a kind of systematic error that is really also prominent at high resolution. I have to keep this in mind, but it's just unfortunate that it's like that. Okay, going back, I think I tried to use the word quality somewhere. I know I failed. So when we talk about quality of data, what do we actually mean? And everybody seems to think of something else, something different when we talk about quality. Quality is just a generic term. The correct scientific term in the natural sciences is to say we have either accuracy or precision. Yeah? Okay. So quality is not the right word. We are always talking about accuracy or precision, as Jim already said, of course. And these two figures have been, I took them from Bernard Rapp's book. And so the left figure shows a situation, an experiment where we measure a quantity, or let's say in two-dimensional space, and each of the blue measurements here represents one observation, and it has x and y coordinate. And if we take the average of all of these, we get this red thing here, and this is actually very close to the true value, which is at the center of the crosshair. I think this is just an explanation for this figure. And it's supposed to show to us that in this case, the observations have rather low precision, but their average may be very close to the truth. So the accuracy of the merge or the average data can be high, whereas the precision of the measurements is not so high. The other situation that we also encounter in practice is shown here. We have many observations that are very close together. Yeah, so the precision just measures how close are these measurements, and their average is also, yeah, well, it's shown here, but in this case it's far away from the true value. So we have a rather large systematic error here that pulls out the measurements to the upper right, this figure here. So we can distinguish in, okay, so maybe let's pull this up. Anyway, so Jim already has explained this. So when we talk about accuracy and precision, we can always easily talk about precision because we only need the measurements to come up with a measure of precision, right? But if we talk about accuracy, we also we use the word true value. So where does this true value come from? How can we know the truth? So if there is some systematic error that we don't know, then the true value cannot be found from the data themselves. It's clear because it's a systematic error that pulls the measurements away is not known. But in many cases we have a good model, a molecular model, that gives us some f-calc, or we can square them, f-calc square, and we could assume that the errors of the model are not correlated with the errors in the data. And in that case, a good model may be an approximation to the truth, but ultimately it would be better to have a model, for example, to verify that the program gives the right answer. We should do proper model calculations and not use crystals, but rather calculate what we expect from a given PDB file. So we can always easily calculate precision from our data, but accuracy cannot be calculated usually unless we have a very good model or we do model calculations. So they always differ by the unknown systematic error. And you should really realize that all our data quality indicators, they estimate the precision of our data, not the accuracy. But ultimately, we want the accuracy. Yeah? So this is the big difficulty that people have. They look at the indicators and they want the indicators to be beautiful. Let's say table 1 gives us beautiful or merge or whatever, or I over sigma, and they mistake it for talking about accuracy. But this is not the case. So a numerical example that I tried to come up with is, maybe we can skip this, but whatever. Let's assume we would like to determine pi, and our measurements are just these here. And you see, they agree very well with each other, but some unknown systematic error happens, so they are far away from the truth. We can calculate the precision. It's just a relative, for example, as a relative deviation from the average value. And I did this here, and it's only 0.05%. This is the precision of these data. But the accuracy of these data, calculated as a relative deviation from the true value, is 13%. Okay, this shows you an example of high precision and low accuracy. Now, conversely, try to determine this constant once again, but your measurements are here. This is a situation of low precision but high accuracy, because the average of these is very close to the truth. Whereas the precision is low, if you calculate it, it's higher than it is here. So yeah, that should make clear that highly good value for precision does not always mean that we also have a high accuracy. So now comes the next concept: unmerged data precision and merged data precision. Yeah? We have seen we can always calculate precision, not accuracy. Let's do it for the unmerged data. Let's do it for the merged data. So what can we do? Precision indicators for the unmerged data. Try to collect them here. I over sigma of individual reflections averaged over a reflection shell. That is what data processing programs give us. And then there's our merge. This is the same as our sim, by the way, same formulas, but different name. And here we see it's just a relative deviation from the average. It's just the definition that I had on the previous slide with the numerical examples. This is what everybody would come up with. So intuitively, this makes a lot of sense to calculate the precision in this way, right? And it's just a relative, because it's a relative quantity because it's normalized. Now it turns out that, and this we published in 1997, that this formula depends on or gives other different values if the multiplicity of the data rises. So for higher multiplicity, it gives higher values of our merge. This is not really what we would like to see. So we found that a factor that is included into the formula takes care of this. So this is then our means. So since then, our merge should not be used anymore because this is more reasonable as a precision indicator because it does not also depend on the number of measurements that you're doing. But people have been a little bit reluctant to use it because the numerical values of this formula are a little bit higher than those from this formula. So this is psychology, sociology, and whatever you like. This is not science, but something else. Anyway, the relation, of course, since these are all looking at precision of unmerged data, there must be some relation between these. Yeah, the relation between our merge and our means is, of course, this factor here. But there's also a relation between the mean I over sigma and our means, and the relation is given. It's simply a factor of 0.8 under some assumptions. Yeah. Whether you put I over sigma average or I average divided by sigma average, it doesn't matter. It's always the same idea here. Yeah? So this can be easily extended to other definitions, like the one that SBGrid's program uses. So now we are going to look at merge data. How do we arrive at merge data? There's a very simple formula. Look it up in the Wikipedia, weighted mean, and it tells us the intensity. In our case, it's just a weighted sum of individual intensities divided by some other factor. And this uses the weights. And the weights, the sigma of this weighted mean is then sigma squared equals this formula. So it's very easy to do. And this is, of course, only really valid if the errors in those intensities are unrelated. But we are always using this formula anyway. So this merging, of course, may improve accuracy and precision. So that's why we do it. So it requires some multiplicity, and if this multiplicity of, let's say, n is available, then the error of the average data will be less than the error in the original data by a factor of square root n. This is just error propagation, right? And so random errors are really unrelated. They are never related, yeah? Because they are just due to quantum effects, and one quantum process does not know anything about a different one. So averaging of random errors always decreases the random error of the merged data. Very nice situation. And this may also work for the systematic error in the merged data, but this is not guaranteed as it is for the random data, because we may always be sampling the same direction of the systematic error. This would be a bad case, but it really occurs in practice quite a bit. So we would like to sample all possible values of the systematic error in a random way, for example. That is what we call true multiplicity. And it requires really to collect more than just the unique part of reciprocal space of your crystal. Yeah? It really requires you to go more than those 90 degrees for orthogonal crystals, for example. So if the errors are, because if the errors are related, in the case of systematic error, they are often related, then we can improve the precision by merging, but not necessarily the accuracy, unless we are really sampling the possible values of the systematic error evenly or at least randomly. So now what indicators are there? So we have our PIM. This is also a variant of the formula that we've been looking at. there's also the mean I over sigma of the merged data, and I've just shown you the formula to come up with these. So both of these formulas assume validity of the square root of n law. So they suppose the square root of n law is valid, which is valid only for unrelated errors. And once again, those two indicators are related by such a formula. Point A divided by so-and-so gives our PIM. So one is not better than the other. They measure the same thing in a way. There's a different way of coming up with the precision of the merged data, maybe by, let's call it partial merging. And I've tried to illustrate this here. So just compare the averages of two randomly selected half data sets. Let's call them X and Y. So our reflections, these are 3 reflections out of 10,000 or so. And in the order of measurement, for example, of this reflection, we get the values 100, 110, 120, and so on, 90, 80, 100. So now we have our dice here. Oh, I'm not too...
Can I ask a question in the middle of your talk?
Yes, go ahead.
So you have RPIM approximates point A divided by I over sigma, but if you go back, you said R measured was the same.
That's a different I over sigma. This is the one of the merged data. This is the merge intensity divided by the merge sigma, the estimate. So we can go back. But then I need another 5 minutes. This formula. This I and this sigma. I'm talking now about weighted mean and its sigma, whereas earlier I was talking about the intensity of individual observations and their sigma. Okay, these are two different beasts.
Thank you.
And they are, for example, in Bernard Rapp's book, they are the same. So it's highly confusing. Everybody is confused, and this is why I harp on this so long. Okay, to get rid of the confusion. Okay, so very good question, by the way. So anyway, so let's call these X and Y, and now we roll our dice. And the dice has 6 sides, and they are either even or odd. So even dice means call it X, odd dice call it Y. So our dice gives us X, X, Y, X, Y, Y for these measurements. So now I can take my calculator and say, okay, 100 plus 110 plus 90, that gives 300, average is 100. Okay, now the Y's are the third, fifth, sixth. So 120 plus 80 plus 100 is also 300, okay, the average is 100. So this is how I come up with an average intensity of 100, both for X and Y. So I have I have partially merged my data set or averaged my data set, but I have now 2 half data set and the individual observations were randomly selected. This is what the programs do that use this half data set thing. Now I'm not using now the square root of n assumption that it holds. This has not been used. I have just operationally defined what I'm doing, and I'm just trying to look whether averaging improves my data or not. So I can do this for all the reflections in my data set. I come up with, let's say, these 2 columns of average intensities, and then I can calculate with them. For example, I can calculate an R factor between the 2 columns, or I can calculate a correlation coefficient on these X and Y values. This is the whole idea. And it's supposed to be more robust than just assuming the square root of n law, because the square root of n law really requires that things are unrelated, but this doesn't. Okay, let's see how these 2 possible ways of coming up with merged precision indicators behave. First of all, I over sigma, the average I over sigma, this should be where the sigma is shown here. It's always a rising curve. So on the x-axis we have the multiplicity here. In this case it's the data range. So I over sigma as a function of multiplicity is always going to rise. Why is that? Because the sigma is always getting lower if you have higher multiplicity. This is very clear from the formula. As soon as you add more terms in the denominator on the right-hand side, the denominator becomes bigger. That means the ratio is smaller. That means sigma squared is smaller. So I over sigma will always go up. And now if you use instead a correlation coefficient, This doesn't use the sigmas at all, it just uses the x and y's, and so this is not going to rise always, but it can go up and down, and in this case we have some radiation damage here at the very high resolution. I think this, the correlation coefficient, if it's constant or goes down, that would be an indication of radiation damage. This is concerning our future panel discussion here. This is why I would say I over sigma has less information about the data than the correlation coefficient has. Yeah? But there is also another argument for this, and I'll come to that in a second. So shall I use an indicator for position of unmerged data or of merged data? There is not a single answer. The answer is it depends what you want. First of all, you must make sure to understand that there is a difference between those two types. Those were the last couple of slides, right? And you don't find this in the papers or in the textbooks. For some reason, confusion is there, but this is probably because no one really ever wrote this up properly. And now, what do we need these for? Precision of unmerged data, for example, can help to decide between space groups. Yeah, you can compare our merge or so in different space groups and decide on the right space group. Or it can be used to calculate the amount of radiation damage and other applications. Then indicator for precision of merged data assess something else. They are looking at the merged intensities and tell you something about what they are, how precise they are. And this is important for anything having to do with downstream calculations. So whenever you use merge intensities to calculate something downstream from data processing, let's say molecular placement, phasing, or refinement, then you are actually interested in the precision of those merged data because you are not using the unmerged data anymore, right? So our merge, for example, doesn't tell you anything about the suitability for phasing. Sorry. So this is maybe a little bit provocative, but it's a completely wrong idea that our merge is going to tell you something about molecular placement or refinement success. It just doesn't work like that. Yeah? It doesn't take the multiplicity into account. We are not using unmerged data in molecular placement. We are using merged data after all. So this is why we care about their precision. So that's a big thing here. So now confusion arises because all those indicators have very similar names. The formulas, if you don't think about the formulas, they look so nicely similar, but they measure totally different things. We always also use a similar formula for our work and our free. Here we have the merged intensities and now converted to amplitudes. So this is talking about something having to do with precision of merged data, and this is that color. Now, many people seem to compare our merge and our work or our free. Or at least the reason why they cut their data at, let's say, 60% our merge is because they would hate to see our work and our free go to 60%. That would be very terrible. But they have nothing to do with each other. Because only our PIM is talking about merged data, whereas our merge or our SIM is talking about unmerged data, so is our MEAS, right? Whereas this is using merged data. So this is comparing one with the other is like comparing apples to oranges. Yeah? It just is not meaningful. Okay, we can also look at I over sigma as I explained. This exists for both the unmerged and the merged data. And now correlation coefficients, however, have only been defined for merged data, and this is CC1 half that I just talked about a second ago, and CC anom, which is talking about anomalous data. So what do we need these indicators for? For example, high resolution cutoff for refinement. So high resolution is better because we want higher accuracy of the model, better maps, but sometimes we find at high resolution we get a higher our work and our free. Other things are important. Which data sets or frames should we include in the scaling? Should we reject some observations and so on? So we are always facing these questions, and we have no good ways of coming up with answers unless we understand what the indicators try to tell us. The reason why it is difficult to use R values, or they are not factors, they are values, is that these absolute differences are terrible to work with. There is no mathematical theory that relates absolute differences to each other. So in this sense, crystallography has made the wrong decision many years ago of using absolute differences. It would have been much wiser to use variances and expectation values instead, but this decision has been made some time ago. You're not responsible for this. But we'll have to live with this maybe for now, but crystallography is really disconnected from mainstream statistics. So it would be good to replace R factors or rather R values by something more meaningful. So, and this is also part of the reason why it's so confusing. You cannot do something sensible with it. Phil wrote not too long ago, our merge is not a very useful criterion. Very good. And the idea that he has is extremely good. Ideally, we would determine the point at which adding the next shell of data is not adding any statistically significant information. So we are talking back to the high resolution cutoff here. So he's proposing to check the next shell of data whether it adds some information. Very good idea. Others have said our merge is useful for making the cutoff. If you read this, they propose 30 to 40% or 60%, but they also mention redundancy, which is multiplicity, the same thing. So the things are connected, are merged, and multiplicity should both be taken into account in some way, but it's poorly specified in some cases. There's also I over sigma, this rule of thumb, who has below 2, this should be the cutoff. Yeah, this is, but this is very different from what it says in the next sentence. Our merge may then reach 20 to 40%. So these two are not really connected in the way that these two sentences suggest, because this one is, the first is talking about the merged data position, the second is talking about unmerged data position, and to take those two into account in those two sentences doesn't really make a lot of sense. People nevertheless deposit data structures where they cut their high resolution at about 50% or so. And now, I would like to present to you some ways of doing improper crystallographic reasoning one way and the proper way. Typical case, you have data to 2 angstrom resolution, so the edge of your detector is at 2 angstrom, you have only 2 angstrom data. So using all these data to 2 angstrom, we get our work of 9 and our free of 24% overall. Your model, you're very nice. Now, if you were to repeat the refinement at 2.2 angstrom, you would get a lower R work and also a lower R free. So this is what leads some people to say, okay, let's cut it at 2.2 because R free and our work are both lower, so that must mean it's better. This is once again comparing apples and oranges, because these two sets of R values don't refer to the same data, and it is meaningless to compare indicators for different sets of data that are overlapping in this case. It's just meaningless. Let's try to do it in the proper way. First of all, we should all agree on one thing: better data should allow you to obtain a better model, right? I don't think we really disagree about this. Second, a better model can be recognized because it has a lower R3. Better model, lower R3, yes, that makes sense. And it should also have a lower R3 minus R work gap, because that means we are overfitting less. So if we have 2 models for the same data, then the one with the lower R3 and the lower gap is the better one. I think that's a good rule. So we can compare model R values, R3 and R work, only when they refer to the same data, yeah? Not to different sets of data with different high resolution cutoff. And now let's take these 3 points together, and we call this the paired refinement technique. That means compare models in terms of their R values, our work and R3, against the same data, okay, not against different data. Now I'll just give one example for this. This is what we published 2 years ago, the same data. So this is a data set giving very high R merge at the high resolution edge, 450%, so 4.5 here. Really weak data. I over sigma is that the gray curve here going, if we look at the inset, that's just the zoomed in part, goes below 1, before 1.5 angstrom. And it's below 2 at around 1.6 angstrom. Our merge is this here. So it's this is 0.6. So it will be 1.8 angstrom cutoff based on our merge of 60%. Our pin is also shown here, but the curve has the same shape. It's just lower by a factor of about 3 or so. So where do we cut these data? And now let's assume we we want to find out which resolution shell still improves our model. This is just Phil's idea in disguise. So we use the paired refinement technique. For example, start at 2 angstrom and 1.9 angstrom, do 2 refinements in parallel, and use the same starting model and parameterization. Then take the 1.9 model and calculate its R values for 2.0 angstrom data without further refinement. Keep the model fixed. The 1.9 angstrom model is fixed. It's just a PD file. Don't refine it. Just get our work and our free. Then calculate the difference between the 1.9 angstrom model and the 2.0 angstrom model at 2 angstrom data. That gives us the difference, and we can plot it. So the red bars are free, and the blue one is our work. And both are negative, so R3 is lower at 1.9 for the 1.9 angstrom model and the 2 angstrom data. So it's actually the better model. Repeat at 1.8, so 1.9 and 1.8. Yeah, R3 is once again going down, so we decide for 1.8. 1.7, in this case, R3 is going down, indicating 1.7 adds some significant amount of information. And also the R3 minus our work gap closes because it gets narrow, it's less, because our work goes up. This continues out to the very highest resolution shell where there is no real significant improvement anymore. So yeah, it's a very nice way of showing that at least out to 1.5 angstrom at each resolution shell adds some information to our model. So now, how does a correlation coefficient help us? So we have seen that doing this paired refinement technique, we find that high resolution data are seemingly good for our refinement, but how can we show it? By looking at the precision indicator for the merged data. Now let's look at the correlation coefficient. It has very well-known properties. For example, we can calculate the significance of a particular value by just looking at the numbers. So, for example, 30% correlation coefficient is statistically significant at the 1% level if there are more than 100 pairs of reflections that go into the calculation. And even a low value of, let's say, 8% is significant at 1% level if there are more than 1,000 reflection pairs. Like in a high-resolution shell, often have more than 1,000 reflections. So we use this in the same way as I've tried to explain it earlier, these random half data sets, and they give you a correlation coefficient that we call CC1/2, and Phil had already implemented this as CCI mean in Scala, which is now aimless. I think you've switched the name to CC1/2 to make it consistent. That's very good. Okay, and now I told you earlier that there is a reason why statistics uses variances and expectation values and not absolute differences. And here we see this in action. By just using CC1/2, we can analytically come up with a formula without any approximations that estimates now from CC1/2 the correlation coefficient of the fully merged data against the true data that nobody can measure. So that's a very interesting concept. By looking at your actually experimental data and doing partial merging, comparing the two halves with each other, we can estimate what would be the correlation of the fully merged data against the true data. So how far away are we from the true data that nobody can measure usually? And this is this simple formula where you can plug in your CC1/2. Okay, let's look at these at lots of these quantities. So the lower one is CC1/2, which goes to, let's say, below 10% at the high resolution edge, and CC star, which is 30% at the high resolution. But already at 1.5, it's on the order of 50%. I over sigma is this curve here. So when we see that the refinement actually improves the model, it's 1.5 angstrom, yeah, CC star tells us, yeah, well, the correlation to the true data is 50%, so that's not a big surprise that this amount of correlation and so this amount of truth in the data is helpful to improve the model. Now, we can also calculate correlation coefficients for our model just based on the f-calc squared against the experimental data. And now these are on the same scale, calculated with the same formula as the correlation coefficient that we use for our data. And so now there is a very simple idea. So CC star tells us how far away from the true data our experimental data are. CC work tells us how far away from the experimental data our model data are. And it is clear that the model cannot be closer to the experimental data than the truth can be to the experimental data. If the model would give us f-calc squared that are closer to the experimental data than the true data, then we would be fitting the noise, because the noise is what is the difference between f-calc, the experimental data and the true data. They just differ by the noise. Yeah? And if our model fits the noise, we are overfitting. So that is the missing link between model quality and data quality. Data quality ultimately determines model quality, at least in the sense of looking at CC work and CC free. We can put them into the same plot. CC star, that's the black curve here, and the dashed blue and red is CC work and CC free. And we see that at high resolution, CC work approximates very closely the CC star curve. So if it goes beyond CC star, if it's higher, then we are overfitting a little bit here. But CC work tells us that it's not so bad after all. We are not really overfitting anything. There's more information in these plots, but I don't have so much time. This is summarizing these procedures. So crystal data, CC1/2 can be calculated just for the observed S squared, and we can estimate what the correlation coefficient between observed and true S squared is. This is what we would call CC ops versus true, and CC star is a very good estimate of this without any approximations. Then we can also say observed S squared and calculated S squared, they are related by CC work and CC free. So easily can be calculated. The link is here between CC star and CC work or CC free. You can just compare the two. There's one more thing here that we don't have time now. So in summary, we should use indicators of merged data precision for answering the question how good these data are for purposes like phasing and refinement. We should not use our merge for things like deciding on a high resolution cutoff, or on which data sets to merge, or how large the total rotation should be, where we should cut our data and so on. It's just not really suitable for this, because we are always interested in the precision of merged data. I over sigma has two drawbacks. The first one, the second one here in this list I already explained, but the first one is the programs, different data processing programs, do not agree on the sigma values because they use different error models. And I think Diederichs nicely showed how you can account for different errors in your model, and that will strongly also influence ultimately the error model, right? So there's no way to get around this. So the I over sigma values from, let's say, HQL 2000 or XDS or MOSFET, they don't, or Star Trek, they don't agree at all. Sometimes they're different by a factor of 2 or 3. So this is not a very nice indicator to use for your table 1, I would say. Whereas CC1/2 does not have these problems. Programs agree. It's the same formula. It does not use the sigmas. It just uses the intensities, which is better in that sense. And it can make the link to the model quality indicators. Okay, some references here. And I would like to thank you for